Não, a acabei da afirmação dele. Nossa,
So let's start the last morning session of this week. As usually, let's start with the plan for today. And the plan is that we are going to start start with problem set discussion from yesterday. And today this is gonna be like, I think quite a lengthy one because I tried to choose the problem in such a way that there is something to be told about every single one here. So we're gonna go through all of them and try to discuss them in detail. After that, well, we'll see how much time we have, but probably we might finish the task candies that we started yesterday. And then if we have some time remaining, we will either have a short lecture or just do some problem solving session. It just depends on, I mean, this is like optional, it depends on how much time we need to do more problem set discussion in the very beginning. In the afternoon, we'll have an individual session like on Wednesday, so it's going to be individual session, but it's not a not competitive one. So you'll be free to ask questions. Actually, I do encourage you to ask lots of questions and try to solve as many tasks as possible. And today there will be more than on Wednesday. So you'll have lots to do in the afternoon. All right. So yesterday's problem set. How about we do it like in the order that we're printed? That's fine? Yeah. Okay, so let's start with a cyclic decomposition. Right, so the problem here was that we were given a graph, a directed one, and the question was, well, we'd like to partition the edges into a minimal number of sets so that the edges from each set form a cyclic graph. So, in this example, we can partition edges into, well, there are lots of ways. Like this can be one partition and this could be another partition. And we get two sets which are both acyclic. In case the graph does not have any cycles, then the easiest partition is just take one set and include everything there. And the goal here is to find the minimum number of sets in the partition and then output them. So this is a tricky one because it looks like an extremely hard problem, but you just have to believe that it's not really a hard one. So there are two cases to consider basically. One case is if the graph is acyclic, and then this is easy, right? You just output the graph as the only element of the partition. Second case is that when the graph is not acyclic. And it turns out that then the answer is 2. Why is that? Well, let's order the vertices on the line. Arbitrarily. I mean, this is not direct, it's getting directed both ways, right? And now I've drawn two acyclic graphs. One consists of edges going right, and the other consists of edges going left. They are both acyclic, and we can output them. Like first one as the first element of the partition, the second one as the second element. So I think the way of getting here is, well, you might see it like in the very beginning, but if you don't, and I think it's quite difficult to actually observe that immediately, you just have to play with data and solve some small examples, and once you start solving them, you'll see, hey, I can always get only two elements in this partition, so maybe that's always the case, and I think this was the way to get it solved. And then once you have this hypothesis, I guess you can get to this point. Okay, guys, you've missed the first task. We're now gonna start the second one. That was cyclic decomposition. The second one is divisors. Here, you're given an expression like GCD of LCM of 3 of GCD of X of Y, then it's LCM Y 13 something. And so basically it consists of constants, variables, and the greatest common divisor and least common multiple functions. The functions were all binary, and we assumed that every number, we're given this and we're given a number n. Every variable and constant is a divisor of n. The question was, is the expression constant? Meaning, if we substitute the variables with any divisor of n, we only care about divisors of n, would we always get exactly the same number? Is there anyone who would like to share the solution? Okay.
Well, so basically, when you have the GCD of a variable and a constant, it's called k. All the information you get is that, well, the GCD divides both x and k, so it must be a divisor of k. In which case you know k. And when you do the LCM of GCD and the constant k, all you know is, well, basically the same. The result is a multiple of k. So this is all the information you get when you do these two operations. So basically, what I did was to store for each, to calculate for each expression, the number you know, it's a multiple of, and it's a divisor of the most restrictive one. Like the largest number you know, it's a multiple of, and the smallest number you know, it's a divisor of. So, and it has a very nice property that when you do, when you calculate the GCD of a number that you know that is a multiple of A and a divisor of B, and a number that's a multiple of C and a divisor of D, well, you know that this number must be a multiple of the GCD. It must, well, yeah, it must be a multiple of the GCD of A and C.
The GCD of A.
Because, well, you know it's a multiple of A. And it's a multiple of C. This one is a multiple of A. This one is a multiple of C. So the GCD of A and C must divide the result. So it's a multiple of the GCD. And the same property holds for the LCM, like the inverse. You know it's a, so the result of this is a multiple of GCD of A and C, and a divisor of the GCD of B and D. And the same holds for the LCM, just swapping, just changing GCD for LCM here. So basically for each expression you calculate these two numbers, and then at the end you see if the resulting number is a multiple and a divisor of the same number. And if so, you know it's a constant. It doesn't depend on what are the values of the variables in the expression. And otherwise, it depends on the variables. And all the information I have about the variables is that they're multiple of 1 and a divisor of m. And about a constant, you know that it's a multiple of the value of the constant and a divisor of the same value. That was it.
Right, that's the way to get it. Let me show also some another way of looking at it. This would actually would give us like a super simple solution to this one. So I think in other words, what you were saying is that these expressions like that are in some sense monotonous, meaning that if the arguments, if the variables are bigger, meaning they're multiplied by something, then the result of the expression might only get bigger, right? I mean, if we have GCD of two of x and y, if we multiply one of them by some number, the result may just be bigger. It cannot go smaller, right? And the same goes for LCM, right? If we multiply one of the arguments by some number like a times x, the result might only be bigger, meaning that this is a multiple of this thing, right? And the same holds for GCD. And if this is the case, then what happens here is that if we're if we substitute bigger numbers for the variables, we cannot get a smaller number. If we substitute, if we have some assignment of variables and then we multiply those variables by some numbers, then the result of the expression is a multiple of the initial result. So what we can infer from that is that we can evaluate expression substituting 1 for every variable. And then we do this again, substituting n for every variable. And we check if they're equal. And if they're equal, then the expression is a constant. If they're not equal, the expression is not constant. And that's like, and this gives us also a simple solution to that. The input was given in a recursive form, so you can basically write a recursive function that evaluates the expression and computes what you need to know. All right. So then, let's move on to the third one, the telescope. Okay, so let me ask you again, is there anyone who'd like to discuss telescope? Any volunteers for that? Okay, so let me take this one. Right, so the task here was that white man is standing on some hill, looking at the sky, and at some time moments, meteors are falling. X means here a falling meteor. And there's a telescope there. Okay, this is the sky, so this will be some telescope. And somehow, Whiteman knows what time the meteors are gonna fall. The fall of each meteor takes exactly 1 second, so that's why I'm drawing an X, which is this white here. And he'd like to, and Whiteman would like to watch the meteors, and he can do that using using a telescope. And in order to do that, he has n points with values Ci, which are at most 28, or n is at most 100. Sorry, it's you got m points, which is equal to 10. I'll move it here. And number of meteors is almost 100. And now, inserting the coin after inserting a coin CI, the telescope, well, this is a very old one, it gets stuck, meaning unusable for r seconds, and then works for CI seconds. So, in the example, if, for example, Byteman inserts a coin of the value of 3 in this moment, and say r is equal to 2, and the coin value is 3, then the telescope is stuck for 2 seconds, and it's working for the 3rd second, so he can watch the first one. And then, well, in the example, the coin values were, let me see, 2, 5, and 1. Which makes them, no, it's okay, it's just 1. And then he inserts a coin of value 5 here. And so the telescope gets stuck for 2 seconds, and then he can watch the sky for 5 seconds. And then he inserts another coin, a coin of value 2. The telescope is stuck for 2 seconds, and then there are 2 seconds to watch the sky. Okay, this is the task statement. And now the question obviously is, what is the maximum number of meteors Byteman can see? Right, so once you see a task like that, I guess the first association is, okay, this is going to be some kind of dynamic programming, right? I need to possibly consider all possible subsets of coins, and maybe the prefix of the meteors, Byteman is going to see it, and so on. So let us think of the partial information we have here. Like, we're going to construct the solution from left to right, and at some point, let us think, what do we need to know about the solution, so that we can, well, first extend it, and then the second use dynamic programming. So at every moment, we'd like to know what is the subset of coins that have been used. Secondly, how many meteors Byteman has seen? Third would be, well, okay, so he has used some coins, he has seen some meteors, but then the third thing that is important is, what is the time he might, well, what is the earliest time he might turn the telescope on again? Or using telescope again. Okay. Right. So these are the 3 things that describe a partial solution, and we're kind of would like to consider all possible situations, like every possible subset, every possible number of meteors, and the earliest time for using the telescope again. But since the question is asked, is what is the maximum number of meteors Byteman can see? The obvious association here is, okay, assume the Byteman has used some subset of coins, and then has been using telescope up to some point. I mean, meaning that he can start inserting coins at this moment now. And in this situation, we'd like to know what is the maximum number of meteors that Weissman can see. So this is a natural approach, but it's actually not the one that gives you a good solution. So the trick here is to use an inverse approach. So our dynamic programming would be, well, for a subset of meteors, and the number of meteors seen would like to know what is the earliest time at which Weissman can use the telescope again. Right, so, yes?
Subset of meteors or fancy subset of...
Oh, sorry, yeah, it's coins. So this is, which coins are used? Thanks for that. So, if we know which coins were used, and if we know how many meteors have seen, the best situation for us, if we can continue our observation as early as possible. That's why our goal is to minimize this, right? This is the earliest time, and it should be quite clear that the earliest time is enough. I mean, we can start using the telescope at this time, but possibly also later, right? And now, what remains to be said is how to fill this in, right? So, assuming that we have a state, what are the transitions that we can make? So, like if we have a state like this, what kind of moves can we make to get to the next point? And now there is a simple observation for that, which is assume we have a solution in which these are the times when the telescope is used, including the time that it's stuck. And there are some meteors here. So let us take this optimal solution. Like this maybe. Let us take this optimal solution and modify it by moving these intervals to the left as much as possible. What does that mean? Well, in this interval, I can start actually using the telescope a few seconds earlier, because I would still see these two guys even if I start using the telescope before. So I can move these intervals as much to the left as possible, up to the point where, well, either I hit the previous interval, or so one case is I move this guy until I hit the previous interval and I can't move anymore to the left, or there is a meteor I see in the very last second, so I cannot move anymore because I'm going to lose this one. So the observation is we may assume we use the telescope either right after the telescope switches off, so meaning the previous interval finishes, or so that there is a meteor in the last second, it is working. And now this gives us a way of adding transitions here. So if we have a state like this, so we know the subset of points and the number of meteors and the earliest time we can start using the telescope again. So it's now time to insert the next coin, and we can there are n coins to choose from, right? We can use it's a state, and from this we have to choose a coin, and then we have to choose the starting time. So this choice can be done in m ways. This choice can be done in, well, every choice there is. One option is to start using the telescope right just as soon as possible, and the other option is that it finishes working at some meteor. So there are at most 1 plus n options here, and in this way from one state we get to a new state. So since the number of states is equal to, well, subset of coins, there are 2 to the m possible subset of coins times the number of meteors we can see is n, the number of transitions per state is m times n. We get from this the running time is 2 to the m times n squared, which, given those limits, is actually really fast. There was also a different solution that had, well, this polynomial was smaller, but it had a factor like 3 to the m, and I think it was also more complicated, so I think we may stick to this one. Right, any questions? Okay, good. So let's move on to matches. So I've seen there were some good and distinct solutions for matches. So is there anyone who would like to discuss this one? There is one tricky solution which I think is particularly interesting, and I've seen you guys have done this one.
Okay, so you have n people and m, and this is games, and then you have the description of the games that has n over 2 n people, and like you divide them, let's say n is 4, you divide them into groups, and these guys are on the first team, and this one are on the second one, and then what you can see here is that if you like make a table for each person, and then you try to describe the participation of this person in each game.
So the task here, right, was
you want to answer if every person has faced each other at least once.
Yeah.
Yes. So let's say you go to the one here, and you put game 1 and game 2, And then you put a 1 if it's on the first game. So 1, 1 is as 1 is on both. And then this is 0, 1. And 3 is 1, 0. And 4.
So 0 means it's played in the second team, right?
Yeah.
And 1 is played in the first.
And you can see that if there's any equal, you think this is a mask, that's a long, because it's less or equal, that's and if there's an equal number here, then the answer is obviously no, else it's yes.
Yeah, so it was all about changing the perspective, right? Instead of checking, is it true for every pair of guys that have played against each other? Let us try to find a pair of guys who have played in one team, in the same team all the time. This is exactly checking the opposite. And so for every guy, remember the teams this guy has played in, and since we can remember all information for a guy in 50 bits, we get like a list of 50-bit number, and we have to check if there are 2 equal numbers on this list. So that was the easy and tricky solution. You might have also done this by trying to simulate what's going on. So you basically had groups of guys who have not yet faced each other, and after every game you would divide those into smaller and smaller groups. This would also be doable, but I think it was a bit more complicated. Right, so then let's go on to fuel. Okay, so here the input was a tree. Graph with a connected graph with n vertices and n-1 edges, and we got m units of fuel, meaning that we could start at any point and make m steps. The length of this red path is m, and the question was how many distinct vertices can we visit? Okay, so we have to look at what our group looks like. So let's draw like some abstract route. We're going somewhere, we're going back, going somewhere else. And so on. Okay, so what can we see here is that, okay, well, assume that we do not finish in the same spot as the one that we have started in. So what happens here on every reasonable route that we have went through some edges once, and we've went through some other edges twice, and then it's one this direction, and then the other time is the other direction. But the edges that we have went through only once, they form a path. These are the edges that were visited only once, and they form a path. If we have started in the same, we finished in the same place as where we started, this would be like a path of like 0, so it's still kind of a path. Now, what we'd like to do is, because our field is limited, we can see that we're kind of going to see more if we're not going to use the same edge twice, right? Because every time, every time we're making a step here, we're visiting a new city. So that's great. We add 1 to the result. And the same happens here all the way. And actually, for every edge that we visit the first time, we increase the number of cities that we see, right? So, so our result is equal to m minus the number of edges visited twice. Does that make sense? Okay, so because of that, we'd like to minimize this. We would like to visit as many edges, visit once as many edges as possible. But since those form a path, then it pays off to start to use the longest path in the tree and visit exactly the edges of the longest path in the tree exactly once. So the algorithm would be like A. Follow the longest path. Okay, so let's say this is the longest path, and we have followed this one. So we'll spend some units of fuel. But now we have some more units of fuel remaining. How do we spend those? Well, for every 2 units of fuel that we have, we can visit 1 more vertex. Yep, like wherever there are some edges connected to this longest path, we can use exactly 2 units of fuel to visit 1 more vertex, right? So we're going here, but then we make a detour, enter here, and go back. And then we have still 2 more units of fuel. We can visit this vertex. And then if we have still some fuel remaining, we can visit this, and so on. So for every 2 remaining units of fuel, we might visit additional vertices. So the algorithm is like first find the longest path and follow it, and then for if there are k units of fuel remaining, you can visit at most k over, well, you can visit k over 2 vertices. Vertices 4, okay, if they exist. We can visit that much, well, until we run out of vertices. And so maybe the only difficult part is how to find the longest path in the tree, and this is actually quite simple. I mean, I'm not going to prove this one. In order to find the longest path in a tree, you can just make shortest path computation from any vertex x. Then you'll reach maybe it has to be a leaf. Okay, to be sure, let's assume it's a leaf, but that might not be necessary. So do a shortest path computation starting from any vertex x. You reach a vertex y, and then the vertex which is the furthest one from y, the vertex z. These 2 vertices are connected with the longest path. This is probably the easiest algorithm for finding one. Okay. Next one. Okay, let me skip code per substance for a second. Let's go to completely different words. we'll get back to the subsets. And this was a hard one. And there are actually three completely different solutions here. That are here, right? Still, I'm really bad at spelling. So, two words are completely different if they differ at all positions. And we have a list of words of like 5. And the goal was to find, the pairs of completely different words. There were 50,000 words in the input, and the goal was to find, the pairs of different ones, but if the number of pairs was bigger than 100,000, then it sufficed for us to output just that many. So these two numbers, these two words are completely different. They differ in every possible positions. These two are not. There is an E in the second positions in both of them. And the same goes for these two. They have a common letter B here. So for this example, we only have one pair of completely different words. All right, so there are 3 approaches here. And I'm going to show you 2 of them and just mention the third one. The third one is complicated. So let me show you the simple ones. So the first approach would be based on, this would be a randomized algorithm. And we're going to use a technique from the lecture on Wednesday. And in order to do that, we'd like to find a simpler variant of this problem. So, which parameter can we change so that the problem becomes simpler? Excuse me? Yeah. N is one of the choices, right? I mean, if N was small, we could use brute force, but we're actually going to need something else.
Change the letters.
Change the letters. What do you mean? Actually, this sounds good, right?
Or numbers. Like if you sort through completely different binary numbers.
Oh, binary numbers.
Then the XOR would be 1, 1, 1.
Yep. So what you're saying is the problem is easy. If the alphabet is just 0 and 1. Right here, the alphabet contains lots of characters, so like from ASCII code from 48 to 122, I believe. If the alphabet was small, just 0 and 1, the problem is easy, because then if we have a word like this, then there is just a single one which is completely different, and it's the opposite. And also, if the alphabet is this big, then there are just 32 different words. So this is like very easy. Basically, there are 32 different words, which we can think of as numbers from, like a 5-bit number, so the numbers from 0 to 31, and then a word is completely different from its complement, which means that the corresponding number is completely different from something like 31 minus the word or something like that. You can translate this into number language. But the point is that for a small alphabet, this is a very easy one. You can easily find the completely different words, and there are just 30 different possible words that can occur. So now let's try to reduce this problem randomly into this one. How do we do that? Well, we do as follows. We'll need 5 random functions. And each function is from the, well, let's say, this is the usual notation. Big sigma is the alphabet. Let's assume, for simplicity, that this alphabet is like from A to Z, maybe, and also contains digits. There were more options possible, but let's make it simple for the description. So these 5 random functions would go from the alphabet to the numbers 0 and 1. And then, okay, I can create a function like this at random, meaning so I'm doing something like, okay, f1 of A is 0 or 1 randomly. And I just toss a coin and I set one or the other. And then f1 of B is 0 or 1. I toss another coin. And I keep doing that, and I define f1 until I define f1 of 9, which is also 0 or 1. And what I do now is that after I created all those functions, I use the I function for the ith letter in each word. So, and then for each word, x1, x2, x5, change it to f1 of x1, f2 of x2, f3 of x3, f4 of x4, and f5 of x5. So in other words, I'm looking at the first position for every letter in the alphabet. I assign randomly 0 or 1, and then I change like all A's into something I've chosen for A, and then all B's I change into something I've chosen for the letter B. So the same letter in every column is consistently mapped to 0 or 1, but it's independent for any position. I mean, I do a different random choice for every position now. And what happens now? There is a spider here. So I have a new list of words, which now consists only of zeros and ones. So let's say basically what I did is like a map. So from a word X, we get capital F of X. This is how this mapping works. So now the key thing is that if X and say X and Y are completely different, and then I'd like to relate it to F of X and F of Y being completely different. Which way is the implication going here? Okay, so you can see it already. yeah, it's going right to left. So if these two are completely different, then surely the original ones are too, because you know, if there is a 1, if there is 1 and 0 here, then those two symbols for sure have originated from different letters. We use functions, so if the values of functions are different, then the arguments must have been different too. It doesn't work this way, obviously, because this is not equivalent, but it does work this way, and this is exactly what we need. Now, what we should do now is the analysis. So the algorithm is, one step is, obviously we're going to repeat it. So we randomly change words to binary using this algorithm, and then we find pairs of completely different words. Now, what is the probability that that we get the solution? So, assume there is a pair X and Y of completely different words. What is the probability? I'm going to identify this pair in one step.
One divided by 2 to the power 5.
Excuse me?
1 divided by 2 to the power 5.
Yes. So the probability of we find the pair X, Y in one step is like, well, the first letter of X has to be assigned to something different than the first letter of Y. This happens with probability 1/2. And then the second letter of X has to be assigned something different than the second letter of Y. And that's again probability of 1/2. So this thing is equal exactly to 1/2^5, like 1/32. Right, so the probability that I'm not going to find it is 1 minus 1/32. So now, the question is, how many times do I need to repeat? Okay, so it's like I sum over every pair of completely different words. X and Y are completely different words. The probability of we do not identify the pair X, Y in, say, T trials or T repetitions. And I'd like this number to be small. So I'm going to repeat T times. And then I have to choose T in such a way that after repeating T times, the probability of not identifying a pair in T repetitions is extremely small. I mean, this is a sum with possibly n over n squared elements. So this thing here has to be, sorry, this is n squared summons here. So this thing has to be smaller than, well, 1 over n squared, so that the sum is small altogether. So since in one repetition, the probability is like 1/2^5, so let's see, it's 1 to the 5. If I raise it to the power 2 to the 5, I'll get something like 1 over e. So that's not enough. So let me raise it to 2 to the 5 to the power of log n. And then this is raised to the power of again. Then if I repeat it 2 to the 5 times log n times, I get a probability of something like 1 over n. This is this thing raised to the power of log n. So this is still not enough, but if I do here times 3, this is 1 over n cubed. So this is the number of repetitions I need. For this many repetitions, this is at most this sum over pairs of completely different words, x and y, of 1 over n cubed. And since there can be at most n squared of them, this is at most 1 over n, which is small. So this shows that by repeating the algorithm, I don't know, 75 log n times, we get a very good probability of, or maybe more, 32 times 3, yeah, like 100 log n times, we get a very good probability of getting the result. Now, we can also use the fact that we only need to identify 100,000 of them and possibly decrease t a bit. But anyway, it has to be somewhere, someone of this order. Yeah.
If n is less than 10, then it's not small.
Excuse me?
If n is less than 10, the 1 over n is not small.
Okay, so yeah, you're right. So maybe a good choice for t would be like max of 2 to the 5 times log n times 3, and let me think. I would say 2 to the 5 times 20. This will give us 1 over e to the 20th power. Right? So, yeah, you're right. I actually, in the solution, it's done this way. So, yeah, that's a good point. So you have to be careful that when n is small, you have to make a bit more repetition. But again, you know, if n is small, you can just run brute force, whatever. It's also feasible. Okay, so that was the first solution to the problem. And there is a second one, and I mentioned it's a completely different one. Yes?
What's the analysis of this?
Excuse me?
The analysis of this.
Analysis.
The complex.
Oh, the running time. Yeah, you're right. So we have that many trials, and in every trial we at every step. So we're basically, I think you're asking about this step, right?
Everything.
You know, here it's just linear, right? I mean, I have to. Okay, this is like the size of the alphabet times 5, because I need to put the functions. Okay, maybe let's analyze it in more detail. So step 1. It's we have to draw, well, the alphabet size times 5 random numbers. That's not a lot. I mean, it's not much. And then we have to basically apply or maybe modify the alphabet. I did that in linear time because I'm just going through this. And then step 2, in step 2, I'm going to be finding pairs of completely different words. So it means in every step, let me think about this one. Okay, I know. So in every step, once we go here, we can be, the running time is proportional to the number of completely different words that we find. Or pairs of those. That's because we basically have like 32 buckets. And as we said, the words that fell into this bucket are completely different from those, and so on. So we are just, after the words are in the buckets, we just iterate for every pair of words here and here, and we just output them. And then we check every pair of words here and here, and we output them. And this is good because once we reach 100,000 words here, we're done. I mean, we know that, okay, we don't have to do anything because we just found the solution. Like this step alone gives us the solution. And if we haven't, then the running time is like 100,000 because this is the limit. So this runs in, I should say something like O of the output limit time. Which is 100,000. And and output limit is luckily roughly the same as n. So this is very close to all n. So this step 2 does not slow things down considerably. Okay. Anything else with this one? Yeah.
Is it necessary for the find functions to be different?
Let me think about it. Yeah, I think the reason for that is that it's for calculating probability. So if the functions were not different, it would still be true that after applying them, if we find a pair of completely different words, it means we have a pair of completely different words in the original data. But let's see, the words were like A, B, A. So, okay, maybe the real problem is like, I needed for the analysis to work. I'm not sure where it fails, but I would definitely not be able to say something like, if we have two completely different words, I want to say, okay, I'm going to identify them with probability 1 over 32 because these guys will be different with probability 1 over 2. And this is an event which is independent from these guys being different with probability over 1 over 2 and so on. And what I'm using here is that these are independent events for the analysis to work. And so the construction just helps me with that. My guess is that the analysis, not only would the analysis not work, but there also might be some some ugly cases in which there will be problems, because I really need this independence here, just to be able to multiply the probabilities here, and that's because these are independent things. Okay, so now let me briefly mention the second solution, which is, okay, it's one that we got from a contestant. It's actually, in theory, it's much slower, but I think it's worth mentioning because it's like, the message here is how to solve a hard task with a smart and simple solution, and you know, which the organizers haven't thought about, because this is exactly what has happened here. So the trick here is to use bit masks and just divide the running time of the brute force algorithm by 32, and this we get an algorithm with first, which is like 32 times faster than the brute force, and also it has an extremely low constant running time because there's this very simple operation being done, and that's why it's actually pretty fast. So I think in practice it's just as fast as this one for the input size we got. Maybe if the data was much bigger, these two would be, yeah, I would probably be able to distinguish between these two, but for this size of data, it's actually, I think, not possible. So what we do here is that from our list of words, we build sets, like a set A, A1A, X. This is a set of words. It contains numbers of words, right? With X and the ith position. And this set is represented as a bit mask. So a bit mask with 50,000 bits, which is something like 6,000 bytes. Something like that. And now we do this for every I and for every x, for every I between 1 and 5, for every x between, you know, for all possible characters that we have. So, for example, for these three words, the set A, first position, letter A is in words, well, it's in words, first one, second one, not in the third one, and this third position, letter F, is in the first word, not in the second one, and it is in the third one. So now, to find words completely different from A, B, C, D, E. Already to find words which are not different, not completely different from this. We just have to compute the sum of sets. So definitely the words which have A in the first position are not completely different, and also the words which have B in the second position are not completely different, and also the words with C in the third position, and with D in the fourth, and with E in the fifth. And since these are represented by bit masks of this size, we can do compute this sum in something like 6,000 extremely fast instructions, and then we can just iterate through the bits which are not set here. This can be done by some bit tricks. So using that, you can get a solution which performs something like 300 million operations, I believe. It's like 50,000 times 6,000, but they're all very simple ones, like or computing the OR of two integers, and that runs very fast in practice. All right. Let me just mention the third solution. I'm not going to describe it. So the third solution here is to use inclusion-exclusion principle, and this one, if I remember correctly, and this one, we're basically able to, we're doing some dynamic programming, and we're able to actually exactly count the number of completely different words and pairs of completely different words, and also from this counting you can kind of retrieve the words themselves. So basically you have to think of the mathematical problem of counting them, and it turns out that there is a dynamic programming which can be used to get this number. Right, let's go on to the next one. Okay, maybe let's do two more and we'll take a break after that. I mean, the two that we do now are actually quite simple to discuss. So the next one is holidays. Holidays is, the task here was given endpoints and VE space with a Manhattan metric. Manhattan metric meaning that the distance between point x1, y1, z1 and the point x2, y2, z2 is equal to the sum of absolute values of the differences. Right. So we're given that, and for each point, find the most distant one. Okay, so what we can do here is try to think about the 2D problem first. So we're given points on a plane, and then for every point we'd like to find the most distant one, and the metric is Manhattan metric. So with Manhattan metric on a plane, a ball of some radius looks like this. It's like a square which is rotated by 45 degrees. And in particular, we can transform the Manhattan metric on the plane into a maximum metric. So a metric in which a ball looks like this. This means that the distance between point x1, y1 and x2, y2 is equal to the maximum value of the difference between the first coordinate and the second coordinate. And in this metric, it's actually very easy to solve the problem, right? In order to find the most distant point, we just need to remember the topmost one, bottommost one, the rightmost one, and the leftmost one. And we can be sure that for all points in the plane, the most distant one is one of the 4 here. So this, when transformed to Manhattan metric, means that it suffices to find the point which is as far as possible to this direction, this, and then this one. In other words, so that the straight line going to the point with this angle is kind of below all points. The same goes for directions. And we have a list of 4 points, and for every other point, one of those is the furthest one. And in 3D, exactly the same thing happens, but it's just a bit more complicated. So in 3D, okay, let's try to draw it. The ball with some radius looks like this. So this is like this is some object that has 8 faces, and they go in like 8 possible directions. So again, to solve the problem, we have to find the 8 points which are the furthest into each of the 8 directions. Meaning, like, you have to find the point for which the value like plus x plus y plus z is the biggest, and then the value minus z, and all. Like we take all 8 combinations of plus and minuses here. For every combination, we find the point which has the biggest value of this expression, and those 8 points are what we're looking for, meaning that for every point, one of those 8 is the furthest one. So that we get a linear time solution here. Now, what I'd like to stress here is that whenever you have a task like that and you want to compute something like this, you might be really tempted to just write one line and copy paste it, or 1 or 2 lines and then just copy paste it 8 times. And I think a good advice here is do not do that. It's like the great copy pasting is kind of the root of all evil that might happen in your program. Especially, I think that maybe the best example here is when you're writing some DFS or BFS algorithm walking in a grid, and you're considering like cases of going right, up, left, and down. So it's often the case that people try to write just one code and then copy it 4 times, change some plus and minus ones, so that they consider all 4 cases. And in the end, I don't know, it happens to me like every second time I did copy paste, I realized, oh, actually the first code was wrong, and I have to correct it, but I have to correct it now 4 times, and then something is still wrong. So maybe one copy was corrected incorrectly, and then the amount of work you do after that is really big, and it's really. I think if you're familiar with how to write those, actually even writing the code without copy paste is faster in the end than copy pasting it and changing by hand. So yeah, this is something I'd really like to stress here. Okay, and the last task before break. This is the task called square words. A squared word squared word is a word. It's a word of the form x So things like murmur, or my favorite one, hot shots. You don't really see it's a square word, but I'll tell you write it, but it really is. It's like hots and hots. Okay. And the task here is given a word of length m at most 1,000. Find the longest subsequence, which is a square word. Now, the main difficulty here was the number 1,000, which turned out to be very misleading to many of you. At least that's what I've heard after the contest. But okay, let's try to solve this one first with any correct algorithm, and then we'll see that we'll get a slow algorithm, and then we'll realize that the slow algorithm is actually a fast one. So the question now is, we have a word, and we're looking for a subsequence which is of the form XX. And the question we might want to ask ourselves, what kind of hint would we like to get in order to be able to find the solution efficiently? And the kind of hint that will really help us is, say that the result is created by taking those elements of the sequence. What we'd really like to do, so this is 1x, the other x, they're the same. So what we really like to know is where is the position dividing them. Because if we know that, well, there is a word x on the left side and a word x on the other side, and they create the longest square word. In the end, we can just find the longest common substrate, the subsequence of this part and this part. And we'll obviously get x as a result, and this would be the result of our computation. So if we knew where this partition is, we just divided the string into two parts, run LCS algorithm on both of them, and we get the string x. Now since we do not know that, we do the simplest thing possible. We just check all possible options. There are just 1,000 of them. So what we do get here is that we have a running time of n, so checking for all possible divisions, times n squared, which is equal to n cubed, which is great, but seems to be way too slow. Way too slow for this size of the input data. Now, it's actually not, because this is an upper bound. And, well, asymptotically, we do get the running time of that much, but the number of operations our algorithm is going to run in the end is not so bad after all. So, first of all, you might think it's like something like, well, 10 to the 9th operations, which is a lot. But then, first of all, what is out of those n runs of the LCS algorithm, which is the slowest one? Well, the slowest one is if we divide it in the middle, and we get like a problem of, we get something like 500 by 500 operations, which is 2.5 times the, which is like 250,000. So repeating this 1,000 times will already give us 2.5 times 10 to the 8th. And it's actually even better than that, because this is the most specific case, In fact, what we're doing here, we're checking all possible places in which we divide the problem into two. So we go from 1 to n, and the running time is something like I times n minus I. And if you do this for n equal to 1,000, and what you get is something like 160 million, which is not bad at all, right? We can afford spending that much time, especially that we're just running a simple DT here with no complex operations. And actually, if you run it, you get a runtime. I mean, in the server, every solution running like that, you maybe half of a second to complete. So this is a solution which is obviously efficient enough. All right, so that will be it for the first part. Let's meet up in 15 minutes, 10 or 15 minutes for the second part of the morning session.
Eles não tinham feito isso. Pode palhaçada também.
Por aí, ó.
reference. The sample drawing. And each reference tag I read wrong.
Yeah, I think this is what we need is to do it rehearsing, right? We write a rehearsing function which read an expression and evaluate it, and then it reads yeah, the absolute is open. No, maybe it's not. Yes, we know. It's not, but it should be like taken as soon as I do.
I got about the how to hold in the row.
I have to think about this one. I had it in my mind sometime ago. Yeah, I'll think about it, and I also have some other solutions for
I didn't understand the part that you remove the I don't know that our like I know that if I propagate this node to this node, I can delete it. But once there are many nodes, they all have a message. This node have a lot of
I mean, by deleting, I got like removing the vertex from the graph. What I'm saying is that this, like, I have a data structure which contains information like these things yet have to be relaxed, right?
but if it's global,
yes, it is global.
so I'm saying that if I relax from here to here, I want to relax again.
No, what I'm saying is that if you relax here, and after the relaxation you discover you can get to the very beginning of the interval, then this, yeah, like if I guess start here, right? Then I can go like this. So I can wait until here and go exactly to start, right? That means it's like this interval is like perfectly relaxed. I mean, I can't do anything better about it because I can just start it, get there as soon as it appears, right? So if I get here and this time, so I delete only those. Only yes. And so when I start relaxing from some point, okay, for the first interval I relax and I don't do anything. But for the second one, I can surely get it. If there is some second one, I can surely get it at the very beginning, and I remove this one, and so on. So with every relaxation, I make like one ordinary one, and others which cause some trouble to be deleted, and those others, you know, their running time is realized by the deletion.
We ask a teacher, what do you mean when you're
I don't your company contest maybe carbon. Actually get really dehydrated but yeah, I mean your contest for training. Okay. For training
Você também queria saber.
Sim, Matheus. Matheus. Como eu não tomei café da manhã, já substituiu o almoço e a janta. Vamos almoçar e tem, né? esperando o Rafa.
Aí eu tenho eu não posso.
Não vira não esse complexo?
Dá pra me ver? Oi? Dá pra me ver?
Dá pra me ver? Sim, mas
Mas a publicidade, não posso falar nada. Que seja o comprometedor e vai ganhar nada.
Eu começo a tomar essa aí eu vou tentar ir aqui para cada um. E chamar.
Daria para
Okay, let's get started with the second part of the morning session. So, as I promised before, let's go back to the problem of co-prime subsets. Question here is, well, we say that a set is co-prime if it's every two elements are co-prime. The question is, how many subsets of the set of all integers from 1 to n are co-prime? So, and the answer has to be given modulo some numbers so that we don't have to worry about overflowing and those kind of problems. This is to make life easier for us. Okay, so let's start with a solution which is, well, maybe it's not maybe this totally simplest one, but it's like a dynamic programming which is kind of not too complicated, and it's like the first step towards getting a model solution. So we're gonna count the co-prime subsets with dynamic programming, and well, the question we have to ask ourselves first is, okay, let's say we have some subsets which are co-prime. So what do we know? What do we need to know about a subset or about a set so that we know what other numbers can be added to this set, right? So what is the information that fully describes the set from our point of view? And this information here is obviously the set of prime factors, a set of all numbers in the set, right? So because of that, we'll be counting the co-prime subsets with a dp array, and it's like it's dp of set of prime numbers and as the number of co-prime subsets in which the co-prime subsets S in which such that the set of all prime factors of all elements of each set is S. I'm sorry, so basically, we have some set of prime numbers, and we want to compute the number of subsets such that if we look at all prime factors of all elements of this set, so this set of prime factors is exactly S. So if we sum all numbers in this array, we'll get the result. This is just the total number of co-prime subsets. So what happens? So what we now need to do is just to fill this array in. Now how to do that? Say we have, we'll be adding, processing numbers one by one, so we're going from 1 to n, and we're gonna, at some point we're gonna assume, okay, we've computed the array for all numbers from 1 to I, and now let us add a number I plus 1 and see how many new co-prime subsets does it create. So say we have processed maybe numbers from 1 to 5, and for example we have that, well, the sets that prime factors are well, no prime factors, there is just one such set, this is an empty set, and then the set whose only prime factor is 2, well, this is 2, and the sets are like, sorry, let me count those. This is a set like this, 1 and 2. There is a set 1, 4. There is a set which is 2, a set 4. Anything else here? The result is 4. And for example, the result for prime factors 2, 3, and 5 would be, okay, we can have 1 and 3 and 5, or we can have 3 and 5, and that's pretty much it, right? We need to have, every set we need to have elements which have all these prime factors. Right, so this is like, and so on, right? So this is this array which is computed for n equal to 5. Now from that we'd like to go to n equal to 6. And what we can do is that when we get 6, then we go through all sets, or through all sets of prime numbers to which the number 6 can be added without violating the coprime condition, and we add. So if we get number 6, then here, for example, we can add number 6 to all sets counted here because it wouldn't violate the condition. But we cannot add 6 to the sets computed here because this would actually violate the condition. 6 is not co-prime with 2, and also we cannot add 6 to any of the sets contained here because there is a 3 here. We could add 6 to maybe sets like this, right? And if we add 6, we get something like, we reach a set whose prime factors are 2, 3, and 5. So in the end, adding number 6 would effectively do something like, well, the number of sets with this mask has now increased by that much. So we can take all those sets and add 6 to them and create sets of this form, and also the number of sets of this mask has now increased by the number of sets whose mask is like this, and this goes on. So some confusion. You want me to explain something? Okay, let's move on then.
The order would be from bigger sets to lower sets.
I don't think it matters because I mean, like we're adding a 6. What is the order in which we can add, right? I don't think it matters because we're only updating sets which don't have 2 or 3. I mean, on this side we only have sets which do not have 2 or 3, and on this side we only have sets which do have 2 or 3. So we won't like add the same number multiple times. So like, this loop will go any direction. Now, let's erase this one. The problem with this approach is that number of prime numbers less than 3,000 is pretty big. So this actually won't work. But what we can do, if you can observe, that we actually do not have to to remember the big prime numbers here. We're simply not going to use those. So we can only have a set of prime numbers which are at most root n. And it's again the count of the number of co-prime and so on. Just like there. I mean number of co-prime subsets such that the set of prime factors less or equal to root n of all elements of each set is S. This is exactly what we'll be doing here. Now, because of this change, we'll have to slightly change the order in which our dynamic programming works. Because now we'll be filling in this array, but for every number for every prime number which is bigger than that, we'll have to consider, so for every prime p bigger than root n, we consider all multiples of p in the same term, in the same step. Why that is? Okay, so we remember this mess here in order not to add like two numbers with the same prime factor. We can't add two numbers which have the same prime factor to one set. But as I said, we don't have the number p in our mass because it's bigger. So we can take a look on all multiples of p and consider them at once. And we know that to every set we can add at most one of these numbers. Yes, because we cannot add two because they have a common divisor. So what happens now is that we take a look on all multiples of p. We have some, so we have our array dp. And then we perform one step, which is like add all multiples of p, and we get an array dp new, which is an updated version of that after adding all of these. And so what happens here is that we take this array, we add number p, just like we did there, but we don't then reuse the same array, but instead for every set that we create out of number p and some set from here, we count them in this array, and then we take 2 times p, and we take all possible sets from here and create new sets here, and so on. So basically, we do this. So we're creating by taking a set from here and adding a multiple of p, we're creating a new set here, and because of that, so here we have some sets which do not have any multiples of p. Here we're producing sets with multiples of p. But since we're doing this all at once, and we're taking data from one array and bringing it to another array, we're not going to include two multiples of p in the same set. And after considering all multiples of p, we just take this array and we treat it as the dp array, and we repeat the same thing all over again. So, yep. Sure. Let me just think of a way to reword it. So, how about this one? Does this part make sense? Okay. Okay, so like adding a number here is one step, is basically performing a set of operations like this, right? So let me first explain the algorithm maybe then, and then exactly the correctness of it. So here, I'm going to do something slightly different. I'm going to use array dp new here, and in the beginning, initially dp new is equal to dp, and then I'm gonna update this one, right? So initially is equal to dp, and then so what I'll normally do, I'll just take one number, take the array dp, copy it to dp new, perform an add, meaning that some elements of this are added to some elements of this array, and then this is my current dp array. I mean, this dp goes back here, and then I take another number, I perform some adds, I count them here, and this is again my new array. So it's like this, I take array, this is the array before adding some element, this is the array after adding some element, and then after I add an element, this is my current array. What happens here is that I have my old array, and I perform the step of adding all multiples of p before this array becomes my current one. So I perform something like so let me call this thing add number 6 from array dp to array dp new. So another way, we're adding number 6 and we're creating subsets of that contain the number 6 by taking a subset from here, and then all the subsets we create are then counted here, right? So this would be something like right? Something like that. So my algorithm, my original version of the algorithm goes like initially dp of the empty set is 1 and all others are 0. And then for I equal to 1 to n, I do something like dp new equals dp, and then I add number I array dp, and the result is added to dp new, and then dp is assigned dp new. Okay, so they agree this is how the original one works? Okay, the new one works like maybe one step of this one works like so this is one step. And now a step is like adding not one number, but adding all multiples of p, which is a prime number greater than root n. So actually, the new algorithm might do something like, okay, now first do root n steps, or maybe first add whole numbers that have no prime factors greater than root n. And then what remains to be done is to add all numbers that do have prime factors greater than root n. And I'm explaining now how to add all numbers with prime factors greater than root n. And the step of adding all multiples of some prime number p, which is greater than root n. Observe that each number can have at most one prime factor greater than root n. So this really divides me the numbers into joint groups. It works like dp new equals dp, and then for I equals to p, 2p, 3p, and so on. Let's add number I to dp, storing the result in dp new. And after that, after adding all those, dp becomes dp new. So what is the difference between this one and this one? Here, I add one number, ri, and then after that I have the sets that have this number, right? I mean, the only difference between the array dp here and here is that now I am also counting sets with the number I. This is what has changed. Now here, I don't really want this to happen. I mean, I have an array with no multiples of p, and I use the subsets with no multiples of p to count some new subsets. But then the subsets I just added, the subsets that have a multiple of p, well, I don't want to use them. I don't want to extend them with any more multiples of p, because I cannot add two numbers which are multiples of p to the same set. So I take the subsets that don't have the number p, and I try extending them with p, with 2p, with 3p, and so on. And I'm counting all possible extensions in dp new. And that's why I'm doing this thing in a batch in one step, because after adding a multiple of p after creating a subset with a multiple of p, I don't really want to use it I don't want to really extend it with other numbers that are multiples of p. I can start using those subsets after I've processed all numbers divisible by p. So does it make more sense now? Okay, so yeah, so this was really a tricky one. And I think the main message that you have to take from this one, well, the first one is use dynamic programming with masks that represent subsets of prime numbers, and then observe that since any number can have at most one prime factor being greater than root n, we can actually not store the prime factors which are big in this mask, and still run. And actually, you're going to run the very same dynamic programming, but you can show that some of the elements of the mask are not necessary. So now let's try maybe to show the running time. Maybe let's not analyze it like super accurately. Maybe just let's calculate the size of the DP, because the number of states here is what dominates, or maybe the number of states here times n is roughly the running time. So the question is, what is the number of primes which are less than or equal to root n? And so the number of primes which are at most n is like n over log n. So this is something like root n over log root n, which is equal to root n over log n times 1 second, so 2 here. And this is the size of my bit mask, so the number of states is 2 through 2 to root n over log n, which is equal to 4 to root n over log n. And then this has to be multiplied by the n to get the total running time. So the interesting thing here is that this is a problem in which n is like as big as 3000, and what we get is a solution which is totally not, well, it's far from being polynomial. It's also not exponential because this is root n here, but actually if you substitute 3000 here, you'll see that although in theory the order of growth is very big, for small numbers it's still reasonable and it runs within the time limits. Okay, anything more about this one? Any questions? Okay, if so, let's move on to the last task. I let the surprise to the very end. Where's this one too? The task is surprise. We're given a matrix of integers, and the goal was to find the three squared submatrices which did not overlap, or which had the biggest possible sum of elements. So we're given a surprise. The input is say it's n times m matrix with integers and k, which is close to 3. The goal is to find find k non-overlapping matrices with maximum possible sum of elements. Right. And this was like, I don't know, something and m were close to 300. So the first step, k is small, so it's not a surprise, we're going to solve it for k equal to 1, then k equal to 2, and then from there we're going to k equal to 3. So how do we do, what do we do for k equal to 1?
Just class the numerical subset.
Yeah, so like maybe in the very beginning, we can, it's often the case in tasks like that we'd like to pre-process everything we got, so that we can answer questions like, what is the sum of the submatrix? And we'd like to answer some such questions in constant time. And in order to do so, we just pre-process for every cell. What is the sum? Something looking like this, and then the sum of any rectangle is like this. We subtract this, and add this, and we got the sum of elements in this part.
So from now on, I may assume that I can compute the sum any rectangular submatrix in constant time. Okay, so now k equal to 1. And here, well, the result is somewhere. In particular, it spans some rows. Maybe rows from I to j. And if I assume the result spans these three rows, I mean the upper part of the matrix is here and the lower is here, then I just need to find some sequence of columns, some fragment of columns that in total have the maximum possible sum. So I can fold this into an array. So I sum these numbers to 1, these numbers to 1, and so on. I get an array representing here is the sum of cells Q1, Q1, 4, 1. And the same here, it's like this cell is the sum of those, and so on. And in this array, I just find the fragment with maximum sum. And this is like a very standard problem that can be solved in linear time. So if I assumed which rows were spanned by the matrix I got, I can find the result in these rows in basically linear time, because this is just a standard. It boils down to a standard algorithm. Now, not only can I find the maximum possible, the maximum result globally, but like using the very same approach, I could say, what is the maximum result over these lines? So in this submatrix, or what is the maximum result in this submatrix, and what is the maximum submatrix in, basically every submatrix which has the same width, starts at the top and ends somewhere. So I can answer what is the maximum meaning would be maximum sum submatrix within the first k rows. Well, how would I do that? Well, I can easily compute what is the maximum submatrix whose bottom row is this one, and then whose bottom row is this one. Basically for every row, using this very method, what I get is for every row, I know what is the maximum submatrix whose bottom row is exactly this one. And if I have that, then I just go through all the rows, and for every row I compute the maximum of all numbers above. Then I get the answer to this question. Does it make sense so far? Alright, so now this is the time where we can go to k equal to 2. And what do we have here? If k is equal to 2, then the result is like two matrices which are somewhere. And in order to solve this one, we need a simple but crucial observation. If there are two submatrices here,
Then there is a horizontal or vertical line dividing them into two parts. So, what do we get now? Since there is a horizontal or vertical line dividing them, we can use this solution, and for every possible vertical line and for every possible horizontal line, well, we can check, for example, for this line, what is the maximum submatrix on the left side, what is the maximum submatrix on the right side. We can combine those to get a candidate solution, and we browse just through all candidates for all lines like this and like this, and we got the solution for the k equal to 2 problem. And then it's time for k equal to 3. And that's actually not much different. You just need to consider maybe some more cases. So what happens here is that if we have 3 submatrices, then there are 2 options. Either there is a set of lines separating them, which looks like a letter T, or, I mean, this letter T can be, anyway, there is a line, another line hitting it, or there are like 2 parallel lines separating all 3 submatrices. And to solve this one, we need to solve the problem. Okay, what is the maximum submatrix on the left and the right of some line, and also what is the maximum submatrix within some given interval of rows and columns. Now this again can be done very easily, because it's like once we compute for every pair of rows what's the maximum submatrix that has this start and this end row, and similarly for the columns, we can fill in an array that says what is the maximum submatrix that's between some 2 given columns. Here, the things are a bit more complicated, because okay, we can get the maximum submatrix on one side of the other thing, but we also need to find one in a corner like that. And for the corner, okay, let me think for a second. This is an easy one. Maybe you can see how to do this one. I'll have to think about this one. I mean, I solved this task I think twice in my life before, so there's some good chances I can solve it for the third time now. I need 2 minutes for this one, and I'll be with you back with you. Okay, I got this one. Sorry for that. So, what happens here? Hopefully, I'll get this one right. So, but this is the easy one, but it's actually you need one more observation for it. So let me draw it here, maybe. Now we're okay. So what we're considering here is, say, like a pair of columns, because as I said, we're doing something for every pair of columns or for every pair of rows. So if we have these two columns, we sum those rows to an array. We get an array which is like a vertical one. And we're computing the sub-array with maximum sum. But not only this algorithm gives us the fragment with maximum sum, but also for every position, it tells us what is the fragment with maximum sum that ends at this very position. So we know, so it's going to tell us what's the fragment with maximum sum that ends here, 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 and here. So transforming this to this picture, we got the for every row here, we got what is the biggest maximum submatrix which ends at some row and spans exactly from this column to this column, and we're then going somewhere up. And we get this for every row. And using that, we can calculate the value for corners. So for a corner, we'd like to know what's the maximum submatrix in it, because you know, for a corner like this, you have to use the values for, well, from BP, from the corners over here, and then check the submatrix, the maximum submatrix that ends exactly in this corner, and it may span this some number of these columns. For a corner, we just iterate through the number of columns it spans, and we can get the result from here. So as you can see, it's like a huge combination of various DPs, and you just combine them together in order to get the final solution. I think that the most maybe interesting part, or the most important observation here, something that's useful in some other places, is that if you have a submatrices, I think that the case for 2 is especially important. Then you can divide these two by a horizontal or vertical line, and then this allows you to solve the problems for some parts of the matrix, and then combine them to get the final solution. I think this can also be extended actually to k equal to 4, but it's like, again, the same technique, and not more is happening here. This would just be a bit more messy. Okay, it's time for questions now regarding this one. If there are no questions, then let me remind you that in the afternoon we're going to have an individual session, and this is a problem solving session, so you need to get really motivated and try to solve as much as you can. And let me repeat this one again. Use any means you can to solve as many problems as you can. Discuss, ask questions. When you're stuck, don't stay stuck. Just ask for some help. Start discussing, and maybe take with your friends. Just try to do as many as you can. And that's almost it. But maybe, since I think this might be the last time I'm talking to you all at once during the same camp, I'd really like to, well, first of all, thank the organizer for inviting me. So I would really like to thank Ricardo and Rodolfo, and also I'd like to thank the student monitors who helped a lot with logistics. And finally, I'd like to thank you, because I must say it was great fun meeting you and teaching you, and I really hope you'll do great in your new contest. And I also strongly encourage you to keep training and keep up the good work. So thanks a lot, and the session starts at 1 p.m. Actually,
Okay, first of all, it's totally not another practical one. It's like a theoretical concept. But I think, the value is that it just gives some very. It's actually something about how to use some good tricks and a very clever manipulation of parameters to get a solution to a network here. So yeah, it's like a different way of thinking. And I think I might just send it to the mail list. I think I might also be sending some lectures, some notes that I prepared for myself for the lectures, and also the link to some candies, some materials.
C'est de ma faute.
So I think if it's here, then you can just go and ask him right away.